Hello, my fellow RF and microwave circuits and system design engineers. I'm Dr. Mohamed Nezami with another video in my series on 5G sub 6 gigahertz and millimeter wave RF transceiver designs. Okay, and today I'm going to cover the fifth part, which is basically starting the design of a small cell 3.5 MIMO transceiver. Now this is intended for small cell with like up to 1 watt of PA power. The EIRP is somewhere up to like 40 dBm. Now, just in case if you haven't watch the other parts, I have 4 other parts which I had built the background for. So the objective was to build up the all the back information on the background information on the 5G hardware elements of the cell site, primarily the active portion. Excluding the antennas, although we do mention the antenna types and gains. But today I'm going to go ahead and please watch these videos prior to watching today's video or after, whichever. And please, if you don't mind, just click subscribe to the channel. I would appreciate that. Okay, so let's start our design. So again, I introduced myself. This is my phone number. I operate out of Jerash, Jordan. I have many years of RF and microwave circuit designs, board level. If you have any designs that you need to contract out or you need consulting, short-term, long-term, whatever it is, shoot me an email on this address here or reach out to me via this phone number. If you don't have international calls, you can always download one of these apps on Android or Apple and ring me up. You can make Telegram phone calls on this, and you can send audio and text messages using WhatsApp. Okay, so continuing with the objective today is to design a transceiver, MIMO transceiver for one of the FR1 designated 100 megahertz bandwidth transceiver within these bands in here. Okay, so the one I'm going to cover today basically is right in here, which is around 3.3 to 3.8. Okay, so N78 is the band, but it could be scaled to this or this. And next video I'm going to cover one of the other ones, the 400 megahertz beam steered millimeter wave transceiver. Okay, so just at the top level, just to refresh your memory, I know we covered this, the differences between the FR1 and FR2, or the sub 6 gigahertz and the millimeter wave bands. You can see here as a comparison the differences between them, but in any case both of them have MIMO layers. So antenna complexity is basically right here. So you're talking about anywhere from 2 by 2 to 64 by 64 for both of them. Okay, the waveforms are all the same. Okay, basically the bandwidth differences is that the FR1, the sub 6 gigahertz one's up to 100 megahertz, while the other one, the microwave one, or the Ka band one, if you like to call it that, is up to 400 megahertz. Okay, and of course the band of operations are between UHF all the way to 6 gig for sub 6 gig, and then the millimeter waves from 24 to 52, although we usually call it 24 to like 32 or something. That's the most common parts. So today's design is based on what we covered in the previous videos. Okay, so we're going to take off the shelf 4x4 codec chip from Analog Devices, which contains 4 digital to analog converters and 4 analog digital converters, and we're going to go from bits to antennas. Okay, using a bank of 4 transceivers. Okay, so this is what we call 4 transmit, 4 receive MIMO system, meaning because we really, each one of these is a transmitter. Here's 1, here's 2, here's 3, here's 4. And of course, we share the antenna between them. So in this case, for instance, we have a panel antenna, which has 2 columns of dedicated, the slanted polarization plus minus 45 degrees. So the red ones and the blue ones are for different polarizations. So this transmitter transmits 2 plus 45 degrees and 2 minus 45 degrees, if you might say. Or I'm sorry, yes, 4 of them total. Okay, so we're going to build one of these today. Okay, so we're going to build one of these today at the system level, of course. The intention is that we build the system, verify it using Pathwave SystemVue modeling. And then once we prove that, we select all the components from the off-the-shelf components that you can buy through distributors like Mouser and DigiKey. And then, of course, the way to develop this is you have this board in here. I'm going to use the same drive level of these DACs. And today I picked up they generated 3.5 gigahertz out of the DACs is at minus 18 dBm. Okay. And that's backed off about 20 dB or so from the full scale capability of the DAC to accommodate the waveform, peak to average ratio, to accommodate predistorter if there is one. Now, by the way, from last video, we coupled the PA output to the receive side, and we were going to use this to do some kind of calibration for the transmit path, where you can, do phase alignment, or you can do a lot of other things like automatic power control, linearization, predistortion linearization. So, but for today's transceiver, I'm not going to have that in here. And this part here is just a passive coupler with a fixed attenuator, and then the basically a switch. Or in fact, you could simplify this and use a 3-way splitter or a 2-way splitter. And of course, this does not impact the noise figure of the receiver because it's in the back end. So instead of using a switch, you could couple this, and this is usually high signal level out of the PA. So you can afford having even a 10 dB coupler or 6 dB coupler if you want, for instance. So let's go ahead and pick components that we're going to interface to this chip, starting out with the balance, and then the filters, the amplifiers, the circulator, all the various form of filters, and in the receive path, we're going to have the switch, which switches off the receive path from the antenna to protect the LNA. We're going to a 50 ohm load in here. We're going to pick this switch. We're going to pick the LNA. We're going to pick all the receive. And the good thing about this, it's all the same frequency. That's the beauty of TDD, time domain duplexing, is that receive and transmit, they both operate at the same frequency. So you can pick up the same components, except of course the PA. Okay, so here is the system in simplicity entered into the Pathwave SystemVue. Okay, all these blocks in here have the nonlinear spreadsheet system parameter file entered into the SystemVue, and the S parameters as well. Okay, and then so for instance, we start out here at the transmit. Let me just go to this, this is basically what we have. So we're going to explain it using this. So we have all the filters, all the S parameters, and then the system files in here are all loaded. So if you can come into any of these in here, you can see that we have a spreadsheet. The file is loaded from here. That's what contains the model. So we start out here. This is mimicking the DAC, and right now we're basically playing into the transmitter a signal, a CW signal, We started out with CW, and then we're going to verify it with 100 megahertz actual N77 waveform. That's going to be another video where I would verify the performance of this transmitter EVM and spectrum containment using the mixed baseband RF simulation capabilities of the Pathwave. So that's going to be another one. And then the RF level at minus 18 dBm. Okay, so we start out with this system. We go first. We have the first thing we have here is the DAC that we have is differential output. So we're going to use a balun to a single-ended. Okay, and what I did here is I fit the signal in here on one side of the balance, and then the other one I terminated. Okay, so you just keep in mind that you have an offset of 3 dB in there. And then we, so this is from a Zinger, this is a Zinger component, and you can see that right here, that's this here, that's the Zinger balun. Okay, what I did is I placed a figure corresponding to every one of these components if it's available. Okay, and then of course, let's get back here. And then, of course, the first thing we want to do, we want to make sure that the spectrum is clean from the DAC. So the waveform goes through a bandpass filter, ceramic piece right here. Okay, and this is available from basically various sources like Johansson mini circuits and other CTS and other. So I used, you could use ceramic resonators, but I mean a coaxial ceramic resonators, but I did here is use just a ceramic filter, small piece. All these components in here are reasonably low priced. There are some components that I did use in there which are a little bit expensive, but eventually it will be replaced. And the reason I did that is because of the availability of the model, of the active device model. So all of these components that you can see in here, in terms of hundreds of pieces, they're just $5 each. And I purposely chose all the parts from the United States so I can purchase them easily through Mauser2, www.mauser.com, which is the Mauser distributor of the international section. So once we filter all the signal from the DAC coming in, we filter out all the distortions and the harmonics, the sampling clock, harmonics and spuriouses. Then I threw in this fixed pad just so that I could fix the RF level. Now, of course, you look at this, I don't have any variable programmable gains in here in this path, and that's purposely to make it cheaper because I know I could program the level out of the signal here into the DAC system, and even beyond the DAC in the DSP section, you could scale the signal mathematically so you can play it anywhere from full scale of the DAC down to whatever dB down below. So, and then of course I amplify it up because, as you know, this is minus 18 dBm. So we're going to go up and beef it a little bit up. And once we do that, of course, we're going to create harmonics, and there might be some switching power supply spuriouses that might leak in or something. So I filter it again just to verify that it is clean. And then amplify again. Once I amplify again, that's basically the appropriate level right now. With this pad in here and with the programmability of the digital to analog converter, I'm able to now drive, put the signal into the PA. So to assure myself of flexibility, I added another pad in here, which I could adjust. These pads, by the way, they're bi-pads, so they're just 3 resistors. Okay, so you can just put initially when you build this board, and we eventually are going to have a video on this, how we're going to go to the circuit level, component level in the ADS to do co-simulations, EM and S parameter and harmonic balance all combined together. So with this fixed pad in here, now my RF level is fixed and good. So what this piece in here is a hybrid amplifier, and that's what I did basically. Is a lot of times with the critical infrastructure equipments like this small cell that is accommodating either indoor or outdoor little gathering place, you know, like a little department store or a coffee shop or a small house even. So we don't want to, if one of these amplifiers, which is the most likely part to fail, if one fails, I want to make sure that I still have one. The power level drops by 3 dB, but I still have power coming and a shorter range, lower throughput, but at least it's functional. So, and this hybrid amplifier, basically, it is basically two of these 90-degree hybrids. And then the active device is this package in here. We have two of these devices. So with this now, my level right at this point is close to 1 watt, okay? And then I go through this circulator basically out to the antennas, okay? Now on the receive path, okay, of course, now realize that when we transmit, we want all of these devices to be off. And now there are a lot of newer devices. I chose older devices because of to keep the cost down. But a lot of the newer devices, they have programmability, or shutdown programmability, but that comes at a cost. And so these parts have been in existence for many years. And so what I'm going to do is have the power, the shutdown is in the power regulator that supplies the suction. So what I'm going to have to do is basically, even though you mute the DAC, but you want to make sure that this whole section is off. So because some of the amplifiers might oscillate, even though you're muting the RF from the transmit. So that's how we're going to perform the shutdown. And eventually, if I create this down at the circuit level, you'll see that done in the power regulation section of the transmitter. Okay, so on the receive path, we're going to pick a chip, okay? And the chip I picked is this chip here, and there are two parts in here. One part goes to the 50 ohm load, and the other one goes through and to the LNA section, okay? The LNA section is basically this device in here. What I do is I have this device in here, and then I have a filter, same exact filter I used in here, this one used in here. I amplify and then use that filter again, and then you go through a balance, same balance that I used here, except reversed in the direction, because now we want to go from single-ended to dual-ended into the ADD. And hopefully what I'm going to do is minus 18 here and minus 10 dBm here, plus minus few dBs, it doesn't matter, so you can move around. Okay, so now, just so that I could do the analysis more flexibly on this path wave, so what I did is let's split basically the transceiver, let's split it into a receive path and a transmit path. And that's what I did here. You can see that I replaced the transmitter via 50 ohm load. And then I'm just looking basically right now, I'm putting this as a user equipment uplink signal at somewhere between minus 80 to minus 60 dBm. And then I feed it back in here and see the performance of this. And I added also the block model for the analog digital converter sampling at 4 gigahertz. Okay, so we're going to have 3.5 coming in. We sample at 4 gigahertz, and that places the IF, digital IF, at 500 megahertz. And then inside the codec chip, basically, there's a whole chain of digital signal processing where I take this bassband at 500 megahertz with 4 gigasamples per second. I start decimating and filtering, decimating and filtering all the way to get it to, and then of course the final point where you can rotate it to baseband, and then take it into the data demodulation section. The transmit path is here. Same thing. I replaced the receiver via 50 ohm load and kept the transmitter in here and just looked at the signal. So now the antenna, of course, this is a 4x4 MIMO. So I picked up, typically these antennas, they come in like this for indoor. Okay, there are some that are outdoor as well, but this one here is an indoor Chinese one. And you can see that the gain is somewhere around 8 dB for at some of these angles. Okay, so if you do that and you calculate the EIRP, it comes up to somewhere between 38 to 40 dBm, depends. Okay, per per TL. Okay. Now this one here, you can see the vertical and the horizontal, and of course it's slanted, so the polarization plus minus 45 degrees. And so you could pick up a better antenna than this, but this happens to be like, you can buy this for like, I don't know, somewhere between $10 and $20. Okay, so let's look at the first one is the receive path. So we're going to start out the signal. I'm fixing the signal to around minus 60 dBm, assuming that the antenna signal is minus 60 dBm. And this signal in here, by the time you can hopefully, I hope you see the bottom of the figure for the key of the coloring in here, but the red color is the desired channel power. So which shows the progression of the signal from minus 60 dBm all the way to minus 11 dBm at the ADD, okay? And then it shows you the noise figure as well. So the noise figure is the green one in here. Unfortunately, I didn't display it on the right hand side, but it's about 1.8 dB, okay? And that's typically good, that's okay. Now, I know a lot of the small cells, they're up in the like 2.5, 3 dB type, but that's because they use a front filter between the circulator and the antenna. That filter usually is lossy, is about 0.5 dB. I did not use that filter. I didn't see a need to, because I control the emission, and the pre-selective filtering is done at the individual transmit and receive paths. So that was cheaper, because that filter usually is a high Q filter, and sometimes it's a cavity filter. So I don't see a need for it, okay? Of course, when we get to the actual implementation, we'll find out. But so other things that you can see in here is the yellow color in here, which is the input power 1 dB compression point. And you can see that at the last point from the ADD, the input compression point is minus 40 dB. And that's pretty good, because so that shows that it is a good sensitivity receiver, because you know, for small cell with less than 1 watt, you won't get that high. I mean, there's no way physically that, unless you in the lab point right at the unless you fire up your test transmitter in the electronic chamber or in the lab, right in the same room, line of sight, that you might get that much signal. Okay. Let's see what else. Other than that, so the overall gain is about 50 dB plus minus few dBs. That's what basically we're gonna do for the receive path. Okay. Now the pre-selection, you can see here, it's really nice from 3100 megahertz to 4100 megahertz. We've got nice signal. Okay, so at the power level that I was driving, and now it's minus 20 dB or so. I'm not okay. So you can sweep the front end, and you can see that it starts to compress about minus 40 dBm, okay? And one thing you want to make sure of is that when it compresses, that the maximum allowed power level out of the receive into the ADD does not damage the ADD. So on this level, I check the codec, the ADI 44R codec chip, and the Xilinx system on chip ADDs. This level is tolerable, but you won't get that anyway. Occasionally you might get during testing. Okay, so let's switch over to the transmit side. On the transmit side, basically I start out with minus 18 dBm. That's the red curve here. So this is the budget link for the transmit path. And you can see that the signal goes from minus 18, progresses all the way until it gets to, in this case, 28 dBm. Okay. And the overall gain for the transmit section is about 46 dBs. Okay. The noise figure is 9.7, 10 dB. That's okay on the transmit side. You can see here in the chain that I don't have active devices until 3 components into the chain from the DAC side. Now, if you want to be more sensitive, you could start out with an amplifier right at the DAC output. But I don't want to do that because I have a balance, then I filter, and then I fixed the level right there with a fixed pad. So, and I believe this is programmed to 3 dBs. So that puts it about 10 dB of noise figure. Let's see what else. The compression, the input 1 dB compression point is the yellow one, which is -19. So you can see if I operate at -18 dBm, I'm only 2 dBs backed off, okay? And I'm delivering 28 dBm. So for small cells, you're most likely going to operate at least 7-8 dBs below that. So you're in the 24 dBm, that's typically what the standard calls for small cells. Okay. Now the transmit side spectrum, I do have a little roll off coming from the PA devices. Okay, these devices in here and the hybrid. So, but we're going to fix that, not here. We don't want to start putting passive components at this level. This is a system top level design. We'll fix this issue by doing an equalizer of some sort down in the at the circuit level. And that could simply be just a small, tiny section of a transmission microstrip line that, as you know, the inductive impedance. So as you go higher in frequency, it gets higher impedance and it equalizes this. So, okay. Now sweeping the DAC output from -40 dBm to -10 dBm, you could see that this thing will start compressing at somewhere around 20 dBm, like I said, okay? So the overall specifications is as follows, okay? And they're listed right here. I'm estimating that the transmitter at 30% efficiency, so you're at 3 watts. That's at saturation, of course. When you back it off, down to like 24 dBm, it will be much less than, I would say, 0.7 of a watt. Okay. So let's before we go into the Pathwave SystemVue files to manipulate the design. I just want to remind you that if you have any design, you could send it over. In fact, that very design in here, if you want a board like this, I could deliver you this board. So with a contract, or I could do consultant work at $20 an hour. Okay. Please don't also forget, for people that are in my region, the Middle East, Gulf countries, Saudi, United Arab Emirates, Egypt, Turkey. I have a ANSYS HFSS RF and microwave device training for 3 days. You could come to this site here. I trying to hold it every other month, or I could bring it to you. If you have more than, say, 5 people, I will fly into your location and deliver you this. And basically what we cover there is exactly what's in the videos. Go to my videos, and there's about 30 videos on stuff that I have designed using HFSS. So you can go ahead through these designs in there. And that's basically what we do. I mean, from a Wilkinson divider all the way to an antenna, we cover that. Also, I have 2 sessions, one in the Pathwave SystemVue and one in the ADS, basically. So very much doing the same thing. So let's switch over to the okay. I forgot to tell you, by the way, these are the 4 videos that I did, so you can actually look through these videos. I did mention that at the beginning. Okay, so basically, this is the design right now here. Now, this is the complete design in here. Then I split off the transmit and receive chains in here, okay? Now, one thing I know we forgot to cover is the filters. The way I chose some of these filters, there's tons of filters that are offered in the off the shelf in the market for 5G bands, especially the sub 6 gigahertz bandwidth ones. What I did is I picked this one here from Johansson, okay, and it's like $1 piece or something. And the nice thing about this is that it has a null right at the 2.4 gigahertz, okay? And that's what I want, because usually small cell sites, they might have co-interference with Wi-Fi at the 2.4 gigahertz, okay? And it has also good rejection at the 5.8. Okay, so you can see that they put a 0 at the Wi-Fi. Now, if you try to operate narrower, you can actually go in and start zoning in. They have these filters where you can buy these filters. Okay, and now if just in case if you happen to design this and you see that the spectrum of the transmitter, which we will show in a different video where we the data flow using mixed baseband and RF to see how the spectrum of the transmitter, if the transmitter spectrum envelope does not comply with the regulations, you can always use one of the mechanical filters. I call them mechanical because they're basically cavity type, and they look very sharp. They would have like 90 dB like this one, except they go really, and they can handle tens of watts, okay? So basically I've used this one here. The other filters are listed here. You can see that you can Google them and get a copy of their specifications. All right, so that's it, ladies and gentlemen. Again, if you have any need for RF design consulting, I have few clients that are right now, but I still have a lot of bandwidth to work for. I have one coming up from the United States, which I yesterday had some good news. Hopefully, I'm going to build a longer relationship. If you have an interest, let me know soon, because there's lots of people are reaching out to me to help them out with designs. So be it in the 5G or the KU SATCOM parts, or in the L-band SATCOM stuff. Okay, now this is again, this is Dr. Mohamed Nezami. Again, I thank you very much. Please don't forget to subscribe to my channel. That helps me out. If you can support my channel, there are other ways as well to support me in this effort. Just click on the more information and you can find out how. Until next video, the next video is basically the same design except for the millimeter wave beamforming transceiver, MIMO transceiver. Okay, and we did cover some of that stuff in the past 4 videos, but that one will be putting it all together and show you a transceiver just like that, where we go in and select parts from beamformer chip part, and then the other. And the only difference is there, of course, is that we will take this design, reuse it again with an up converter and a down converter to translate the frequencies up to the Ka band. And the only thing is we have to make sure that we can, with the sub 6G IF section, covers the entire bandwidth, which is 400 megahertz. And that's why this one here is actually a gigahertz bandwidth, even though the waveform is 100 megahertz only. Okay, because essentially when you're designing this, you can always narrow in and use narrower filters to reduce the noise further if you want. Until next time, this is Dr. Mohamed Nezami wishing you the best. Thank you very much.